So, in the last lecture we have been discussing about the citation profile of a given paper. So, what we discussed was that when a paper is published, then after the point of publication the paper initially starts getting a citation at a particular rate which accelerates, then it goes to a steady state in between 3 to 5 years, and then there is a exponential decay in the rate at which the citation is gained by a particular paper. Now, based on this observation, metrics like impact factor etc. were designed, and these observations actually date back to 2001. But then given our data set, we actually did an extensive analysis and we could show that apart from the average characteristics, average behavior, where you observe a single peak in the citation profile within 3 to 5 years, there are 4 other different citation profiles of a paper that is possible. Okay, depending on which citation profile a paper actually follows, or depending on the citation profile of a given paper, you can categorize the paper into at least 5 different classes. One class is our known class, which was also earlier stated in the literature, that is the acceleration, then a steady state, and then there is a decline. Okay. However, there are 4 other classes also. The second class, as we saw, was the multiple peak class, where you can have more than one peaks in the citation profile. So, the paper gains some citation, there is an acceleration, gains some citation, there is a peak, it declines, then again there is a rise in the number of citations, then there is a decline, and this can continue as a ripple effect. There is a third type where the peak is nowhere seen between the first 5 years. Okay. Only if you see quite late in time, you observe that there is a peak in the citation. So, these papers initially did not manage to get high number of citations, they were not popular as such in the initial years after their publication, but then suddenly due to probably development of certain techniques, they became very popular and their citation grew up. Okay. So, then there is another class which is kind of the most unfortunate class actually, where like you see that the citations only decay over time. So, the rate at which the citations are acquired is actually going down and down, declining over time, and as a researcher you would never wish to be in this particular category. And then there is this last category, which is a very interesting category, where you observe that the citations only rise and rise, there is no decline at all, it is monotonically increasing over time. Okay. So, these are papers which are probably seminal papers from the very beginning. So, they have, from the time point they were written, they have been heavily applied and they are still being applied into research. Okay. That is why their citation never falls over time. So, as soon as we observe that apart from the citation profile that was recorded in the literature, we have 4 other different citation profiles also, immediately one needs to revisit and relook into the definition of bibliographic measures like impact factor, right. So, since the impact factor definition was based on this 3-year time year window, this will not hold for papers say in the multiple peak category or papers in the monotonically increasing category, right. So, therefore, there is a need to revisit. So, this is a word of caution, there needs to researchers need to think more thoughtfully or take more thoughtfully the cases of papers which are in other buckets, okay, like monotonically increasing bucket or the multiple peak bucket or the late peak bucket. Okay. Now, we will see some more interesting properties of these different categories. So, the categories, recall, they are monotonically increasing, which we call MONINCR, MONINCR, standing for monotonically increasing. Okay. Peak mul standing for multiple peaks, peak init standing for initial peak, this is like the one that has been hugely observed in the literature so far. Peak late, which is peaking at a later point in time after 5 years at least, and then monotonically decreasing, MONDEC. Okay. So, if you look at all these categories, you see certain interesting observations, you immediately make certain interesting observations. So, on the x axis here I plot the citation value. So, the number of citations that a particular paper in from each of this category gets. Okay. So, if the citation value is between 11 and 12, this is the number of papers from the different categories. If the citation is between 13 and 15, this is the number of papers from different categories. If the citation is between 16 and 19, so in this way you break the entire range of citations into different buckets, into different citation buckets, and you see that the rightmost bucket is the one which actually consists of papers which are mostly cited, which are highly cited papers. So, from 57 to 11,408. So, this is the bucket which consists of papers which are highly cited, and immediately if you look a little bit carefully, you observe that in this particular bucket, in this bucket which actually hosts the papers which have the largest number of citations, the majority of papers are contributed by monotonically increasing, okay, and the peak-late category. So, these are the categories which people, so for the peak-late category, researchers usually do not understand the value of research in the very beginning, but after a point in time, say after 4 or 5 years of the existence of the paper, there is suddenly a surge in the use of that technique. Okay. So, these peak-late papers and the monotonically increasing papers seem to be accruing the largest number of citations. These are the two categories of papers in which the largest number of citations actually are attracted. Okay. Another interesting observation is that if you look into conferences like World Wide Web, okay, and if you look into rest of the other fields, what you observe is that most of the papers that are published in conferences like World Wide Web, they fall in the peak init category. So, that is, so papers which are published in conferences like World Wide Web, what happens is that they have an initial accelerating growth of their citations, then there is a steady phase, and then there is a decline. So, these papers, what I want to say is these papers usually are not very long impact papers, they do not have a long lasting impact. So, basically after 4 or 5 years their citations tend to decline, whereas if you observe the monotonically increasing class, most of the papers in this class are published in computer science journals. So, there is always a debate in computer science whether to publish in conferences or journals. So, this is one shallow indication which tells you that journal papers mostly are monotonically are classified into the monotonically increasing class. Okay. Many of the journal papers actually fall in the monotonically increasing class, that is, journal papers tend to have rise in their citations, whereas a conference paper like typically like the World Wide Web conference, the citation is like the growth of the citation is like only initial, then there is a steady phase, and then there is a decline. So, the point that I am trying to make here is that journal papers tend to classify themselves mostly in the monotonically increasing class, which is like a coveted class, right. So, you only gain citations there over time, whereas conference papers are not like that, they stay for a short time, they are short timers, like they gain citations in the initial years, but then after 4 or 5 years their citations become steady and then finally decline over time. So, this is a very interesting difference between the journal and the conference papers, which becomes apparent from the analysis of our data. So, there is another thing that we study, and that is actually the core periphery analysis. So, basically what you do, you can imagine a citation network or a reference network. So, the one is the contrary of the other. So, basically in a citation network you try to find out what are the nodes which have like one single citation, okay, their in degree is basically equal to 1, you remove all those nodes, okay. Then once you have removed all these nodes, you try to, so this forms your first shell, as if you are like trying to break the network into shells. So, the first shell comprises the nodes which have only one in degree, okay. Once you have removed them, you then remove the next iteration of nodes which have in degree 2, Okay. Then you remove nodes which have in degree 3. In this way you do kind of a shell decomposition of the whole network, and the hypothesis or the intuition is that nodes that belong to inner shells are actually the core of the network, form the core of the network. These nodes which actually are part of the inner shells actually determine the core of the network. So they actually determine the backbone structure of the network, whereas those which are at the periphery are like they have one or two shallow connections, and they do not actually define the core structure, the core backbone of the network. So if you try to do this core periphery analysis, you see certain interesting things happening. So what you observe here, so here we draw the proportion of different categories, like each category, as I have already told you, peak innate, multiple peak, peak late, monotonically increasing, monotonically decreasing, okay, and the last category which is like none of the above 5. Okay. So if you look at the proportion of papers from each category in the different shells, so these are the different shells of the citation network, what you see is that papers which are in the monotonically increasing group and papers which are in the peak late group, these are the most significant groups actually in terms of citations, as we have already seen. So these papers are fast accelerating towards the core of the network. Okay. So in the initial years you see so many of the monotonically increasing paper in the outermost shell. However, as time progresses they migrate inner and inner, okay, into the innermost core of the network, whereas on the other hand like papers from the papers from peak innate group or monotonically decreasing group, they move towards the periphery. So basically papers which are monotonically increasing over time, papers or citations are monotonically increasing over time, or papers which usually see a late peak, those papers actually are accelerating towards the core of the computer science citation network, whereas papers which classify themselves into peak innate or monotonically decreasing category, they are actually fast accelerating towards the periphery of the computer science citation network. So the core, the backbone is majorly defined by the monotonically increasing as well as the peak late papers. So that is the message that I am trying to give you through this particular slide. So now after we have categorized the paper into one of these based on its citation profile, we have categorized the paper into one of these categories. We thought that can this be used in developing certain applications. So and one application that that has become very important in the present day academic world is to predict the future impact of a particular paper. Okay. So if you want to judge the future impact of a particular paper standing at the current point in time, how can you do it? So basically one way to measure the impact is to find out the citations that a paper will get, say in 5 years time or in 10 years time. Okay. That is a factor that you try to estimate given the current data. Okay. Given say a paper is published today, can you predict with high accuracy what is going to be the citation of this particular paper after say 5 years from now or after 10 years from now? Can we do this quite accurately? So this idea is actually called the citation count prediction task, and this is actually very handy when people try to do recruitment. So in the academic world, whenever there is a new application made by a say freshly graduating PhD candidate, so you want to try and estimate the impact of his or her papers, but then this person probably has written papers for 3 or 4 years only, and it is very difficult to judge the impact of this person or the impacts of the papers written by this person within this 3 to 4 years time. So that's why in order to identify what will be the long term citation count of the different papers that are written by this particular candidate, we need a prediction model like this. So where we try to predict the citation count of a particular paper written by a person, say after 5 years, 7 years, 10 years down the line. Similarly, you can use this citation count prediction framework in order to do rankings of academic institutes. Okay. So, if you look at the publication of the current year of the academic institute and try to see what will each of this publication, what will be the citation of each of this publication, say in 5 years or 7 years or 10 years down the line, you from there you can do a precise ranking of the different academic institutes. Say some academic institute, for some academic institute you see papers which will land up into very high citations after 10 years, and there are some academic institutes for which you see papers which will not actually land up into large number of citations in 10 years of time. So, you immediately have a way to discriminate between these two academic institutions, right. So, that tells you why citation count prediction could be an interesting task in itself. So, this is a machine learning task where you can use network structure properties. So, this is a unique actually framework where you kind of unite principles from citation network analysis, network theory with principles from machine learning, by which you do a efficient prediction. So, the standard framework, the traditional framework for citation prediction is the one that I show over this slide. So, you have a set of training samples, there are a set of papers that from where you train your model, okay, and then there is a set of testing samples from which you draw a query paper. Now, from these training samples you extract a bunch of features, okay, and then you feed that into a regression model. So, this bunch of features are some static features which you extract from the training samples. Now, there is a query paper which you also feed into the regression model, and the regression model tells you what should be the citation count of this query paper, say after 2 years, 3 years, 4 years, 5 years of time, by looking into the properties of the training sample and trying to find a match, probable match between query paper and some of the data points in the training sample. So, that is a method where you use a regressor. Okay. So, so we tried to see like whether this framework of citation prediction using, so it is a supervised framework, as you understand. You have a bunch of training samples and then you have a query paper. Based on the training samples you extract features from the training sample, and then you use a standard regression model to identify the citation count of a given query paper. Okay. So, and you try to do this based on a regressor. Okay. You try to see which paper in the training sample or which set of papers in the training sample that your query paper fits well with, and you, based on that you try to predict the citation count of the query paper. Okay. So, now we try to try to advance this particular citation prediction framework by our idea of categories of citation profiles. So, we have observed that a paper can have different citation profiles. So, and there could be at least 5 different citation profiles. Okay. So, a paper could be peak init, a paper could be monotonically increasing, a paper could be monotonically decreasing. So, depending on the citation profile we try to divide our training set. So, this idea in machine learning is called stratification. So, if you look at this slide, so basically you have this training sample which is the publication data set, and you divide this training sample into different sets. So, each set corresponds to one category. So, this is like the initial peak, this is the monotonically increasing, this is the late peak, this is the multiple peak. So, you divide the data set into categories of paper. So, you divide the total training sample into strata. Each strata is composed of papers of only one single category. So, now the next task is you have the same training sample. Using a rule based approach, you divide the training sample into the different categories: initial peak, multiple peak, late peak, monotonically increasing, and so on and so forth. Now, again from the test set you have a query paper. Now, the first step that you do is you classify the query paper using a support vector machine classifier and a set of static features. You first classify the query paper into one of these categories. You try to find out whether this query paper belongs to peak initial or multiple peak or peak late or monotonically increasing or monotonically decreasing. Now, if you have classified this query paper into say monotonically increasing class, then you take only these training samples. Okay, you do not take any other training sample, you take only the class of monotonically increasing papers from this entire data set and train your regressor on that small data set. Okay, that smaller data set. And our hypothesis is that since by first mapping the query paper into one of these classes, what you are trying to do is you are trying to reduce the level of confusion. Okay, so if a query paper is indeed monotonically increasing, and if you have in your data set everything mixed, then there is a chance of increased confusion and there is a chance of misclassification. However, if you already know that your query paper actually belongs to the monotonically increasing class, then learning the features only based on the monotonically increasing features is more beneficial, because in that way you actually reduce confusion. Okay, so we do exactly that, and based on only that subsample, only that strata of the training sample, we do our predictions. And we see, and in doing these predictions we use the standard features that were used also in the traditional framework. So there are three different sets of features: the author centric feature, which includes like the productivity, that is the total number of papers written by the author, the H index of the author, the versatility of the author, the sociality or the mixing of the author. Then there are venue centric features like the prestige of the author, the impact factor of the venue, the versatility of the venue. Versatility would indicate that what is the different fields in which papers are accepted in this particular venue. Then there are paper centric features like what is the generally what is the number of authors per paper, the total reference count of the paper, the reference diversity, the keyword diversity, the topical diversity of the papers. Okay, so all this actually goes into defining the static features, okay, in classifying or classifying the query paper into one of these different strata, and then also fitting the regression model. So so now we have one model which do not use this stratification, where the training sample is directly used to train the regressor, and then this is the baseline model, and then we have this stratification model where we have divided the training set into the different categories, and we compare the performance of these two models now. So we compare the performance based on three different metrics. One is the coefficient of determination, one is the root mean square error, and the third is the correlation coefficient. So these are the three different measures in which you try to find out. So basically what you try to see is your regression model is predicting a citation count, and you also know from the real data what is the citation count of that paper. So what I am trying to say, suppose you have paper P1, P2, P3, P4 and so on and so forth. Say after 5 years, say t equals to 5, from the model, so you have model M1 which is the baseline, and you have model M2 which uses the stratification, and you have also real data. So for each individual paper, say you are standing at some point 1995. So at 2000 your baseline predicts some citation value, say C1, C2, C3 and so on and so forth. Okay. So say for the model M2, what is predicted is C1 prime, C2 prime, C3 prime and so on and so forth. And the real data, from the real data you already have the citation at say 2000, that is after 5 years, is I1, I2, I3 and so on and so forth. Now you try to basically see the extent of correlation between this items, data items and these data items, and also the extent of correlation between these data items and these data items. So, the real data is basically your gold standard, and you compare your model predictions, the baseline predictions with this gold standard data, also the new model based on stratification idea with this gold standard data, and we try to do this correlation, we try to estimate this correlation based on 3 different measures. One is the R square statistic or the coefficient of determination. If you look up the Wikipedia page, you will get a very basic idea of what this measure actually tries to do. It actually tries to plot each point that you get from the model against each point that you get from the real data, and then it tries to fit a line against it, and the slope of that line is basically the R square fit. Now, similarly you can have a measure based on root mean square. So, you basically find out the difference of the squares of these two numbers, and then you take a square root of that, and then you do an average on these two rows, and you also find the standard Pearson correlation between these two sets of data items. So, now based on all these 3 factors, if you try to see, what you observe is that after, if you do the prediction after 1 year, then the R square statistic, when you compare the gold standard data with your baseline, the R square statistic is 0.57, the root mean square is 5.06, and the correlation is 0.61. When you have the stratification included, the R square statistic actually increases manifolds. Okay, the root mean square decreases, whereas the correlation coefficient increases. So, basically observe that if you have a higher R square statistic, that is better. So, that is, which this means that your gold standard data is in high agreement with what your model is predicting. Similarly, if you have a high correlation value, high Pearson correlation, then also you can say that your gold standard data is in high agreement with your model predictions. Whereas, if your roots mean square is low, then you can say, so while the other two are should be high to indicate that there is a high agreement between the real data, between the gold standard data and the model, the root, for the root mean square, this value should be low, indicating a low value would indicate that the gold standard data is in higher agreement with your model predictions. And we see that whatever time point you take, delta equals after 1 year, after 2 year, after 3 year, after 4 year, or after 5 years, in all cases the R square and the rho values are better for the model that uses stratification than the baseline model. So, the simple idea of dividing this training sample into strata or into groups actually gives you a enhancement in the performance of citation prediction. So, you do your citation prediction much better if you base your predictions on the stratification idea. Okay, that is the very simple and elegant modification that we bring into the traditional framework, and this simple modification actually enhances the performance of the system manifolds. Okay, all in terms of R square statistic, in terms of theta, as well as in terms of rho. Okay, and on the right hand side I also show the performance in different citation zones. So, if the papers are low cited, then also we do pretty well. So, you see these are, so bin 1 are all those papers which are low cited papers, bin 2 and 3 are medium cited papers, and bin 4 is the high cited paper. So, you see predictions, doing predictions for high cited papers is easier, while doing predictions for low cited paper, because you have less evidence, doing predictions for the low cited papers is usually harder. But what you see, our model, the stratification idea actually also performs very well in the low citation zone. So, in the low citation zone, the R square with the ground truth as well as the rho with the ground truth is much higher for the model based on stratification idea, whereas theta is much lower. So, this actually shows the power of this simple modification that we have introduced. Thank you.